a bit about we have talked a bit about multivariable functions, we can now go on to learn about how to differentiate them and what does it mean when we do differentiation of a multivariable function. So let's assume that we have this function z equals x squared plus y squared plus xy. And the graph of this equation is kind of like a valley. Now, if you want to find the change of this function as you change x and y's, there are a lot of, if you even choose a single point, let's say 0, 0, 0 on this graph, there are a lot of ways you can change x and y's, and you would get different derivatives, different sorts of rate of change in all of those directions. So instead of being messed up with the number of directions, we choose a standard starting point and build up to understanding what happens if we change x's and y's in specific sort of directions. So let's say I assume that I only change the x variable, and I fix y to be equal to 1. So if I do that, basically I'm taking the intersection of this graph, this blue graph, with this plane with black bars, and the intersection is essentially a two-dimensional curve, which can be written as z equals x squared plus 1 squared plus x times 1. So it's just 1 plus x squared. And for a function like this, it's just a single variable function depending on x, which gives you an output in z. You can easily find out the derivative of this function. So in this case, what you're doing is you're differentiating f, you're finding the rate of change of f with respect to x. However, you're doing it partially. You're not taking all the variables into consideration. You're not taking all the variables that are given to you in the function. You are instead taking a partial derivative, And when you do partial derivatives, you write the sign pronounced as del. So the way you will speak this expression would be del f over del x. And by partial derivatives, that's essentially what it means, is that you are changing one variable, and you are keeping others constant. And what you can do is you can do the reverse of it. You can even change only y and keep x to be constant. But first, let's solve it for this case. If you want to figure out del z over del x, z is the function here, del z over del x for this function, and the way you would proceed with that, you now know that you are keeping y to be constant. So now I'm not really assigning a value for y, we are just saying that y is a constant. So this is just del x of x squared plus del over del x of y squared plus del over del x of x times y. Now, in this expression right here, x squared can be differentiated to give 2x. That's straightforward. However, y squared, since we have assumed y to be a constant, there is no change in this expression, so it just goes to 0. It goes straight away to 0. In the third part of this expression, y is a constant, however x is not, so it's just equal to y. Since the del x over del x is just 1 and y is a constant, you're only left with y being the answer for this third expression. And if you write it down, so del z over del x would be equal to 2x plus y. You can do a similar thing. You can do a similar thing if you want to change y and keep x constant. So in that case, you would write del z over del y, and once you do that, you can just split the entire expression into three parts, and that would be really similar to what we have done previously for finding del z over del x. And once you arrive at this expression, you do the same thing. So x is constant, x is assumed to be constant, y is changing, so this equals 2y. X is assumed to be constant, so this goes to 0. And since x is a constant and y is changing, this would be equal to x. So in the end, you arrive at del z over del y being equal to 2y plus x. Now that's the general idea behind partial derivatives, but to be frank enough, you really don't cover the entire set of directions you can have just by keeping x constant and y changing, or keeping y constant and x changing. There are various sorts of directions that you can always change x and y according to. But as you will see in the later videos, we will discuss that. That's something called the directional derivatives. The directional derivatives. In those sort of derivatives, they are quite easily derived from our knowledge of partial derivatives with respect to x's and y's. So that's a really great application of partial derivatives, and a really fun way to find changes within your graph if you approach x and y's, or you change x and y's according to a certain direction. Now you can extend this analogy of keeping one variable constant and differentiating the rest of them to more than two variables. Let's try three variables. So let me use an example from physics. So you have a resistor, you have three resistors connected in parallel. If you don't know what parallel means, you can just skip this part, and you can just skip how I come to this equation. You can start by taking a look at what happens when I start differentiating it. And by physics, we know that if the resistances of these resistors are R1, R2, and R3, then the equivalent resistance, if this were to be replaced by a single resistance of resistance R, then they should satisfy this equation. Now, irrespective of how we get this equation, we can apply the same principles of partial derivatives. So I want to know what happens if I change the value of R3. So what happens then? So basically we want to find what happens to del R over del R3, keeping all others constant, keeping R1 and R2 constant. Now you can arrange this expression into sort of a clean form and do an explicit differentiation, or you can start by taking the derivatives right away. So you are doing del over del R3 for the entire expression. So that's the left hand side. That would be equal to del over del R3 of 1 plus R1 plus del over del R3 of 1 plus R2 plus del over del R3 of 1 plus R3. So since R1 and R2 are considered to be constant when we are partially differentiating with respect to R3, both of these are just constants, and so the derivatives just are 0 in both of these cases. Now, in this case, in the third part of this, the right hand side expression, you're essentially differentiating 1 over x with respect to x, just replacing x by R3. And we know that it's equal to minus 1 over x squared for the x case, and we can just replace x by R3 again, so this would be equal to minus 1 over R3 squared. On the left hand side, we can do some really fun operations, and namely what we are seeing on the left hand side, it's you can do a chain rule. You can do something that we did in single variable calculus, and that is since in this expression right here on the left hand side, no R1s and R2 occur, and even if they occur, they're just constant. What you can do is you can write this as d over dr of 1 over r times del r over del r3. So basically it's just like canceling out these drs, though it's not accurate to say like that, but you can remember it like that, and we will get to chain rule for multivariable functions as well. But for now, assume that this is true, and assuming that this is true, you get to a point that 1 minus r squared times del r over del r3 is equal to minus 1 over r3 squared, and rearranging gives you del over del r3 is equal to r squared over r3 squared. So that means if I know r1, r2, and r3, then I can calculate the value of r, and I can also calculate what will happen if I change r3, and what sort of slope it would give me if I draw a graph of r with respect to r3, keeping all other variables constant. So that's the basic idea behind partial derivatives. Now we will continue building this idea throughout the few next videos, and I'll see you in the next one.